So in this question here, we're doing question, I believe, 1 from exam 1 of 2020, basically. And this question asks us to find the total current in amps that is going upwards through a horizontal circular disk that has a radius a and has a height h above the z is equal to 0 plane. It gives us the current density vector, and it is in spherical coordinates. It's pretty important that we know this because our integration bounds might change because of this. And in this particular problem, they definitely will. Now, the first thing we should do here is we should notice, what do we have and what are we trying to find? Well, we have our current density vector J, and we're trying to find I, the current. So there's an equation we need to know here. I is equal to the integral J in, and then we have a differential ds. Now, what would n be? Let's see, well, the n normal vector will be positive z hat, the unit vector z, because that is the direction at which the j vector is going. Well, not going, but that's the direction at which our j vector will be crossing the surface. Now, j is going in what direction? Well, given the current density vector, we know it's going in the r hat direction in spherical coordinates. Now, this is very important. The z hat, this z unit vector, is not part of spherical coordinates. This will become a problem, or it might become a problem, or it could be a solution that we need. ds. What is ds in terms of spherical coordinates? Well, ds is going to be rho d phi. Okay. Now, we know ds, we know the directions of each of the vectors. Now we can maybe integrate something. Let's try this. So we take the surface integral, and that entails a double integral, right, of rho d phi of our j vector, which is r hat I over 4 pi r squared z hat, right, our in vector. We have a dot product of rho d phi. Now, what is rho being integrated across or about? Rho will be integrated from 0 to a. What about phi? Phi will be from 0 to 2 pi. Now, we have two different unit vectors, z hat and r hat. Typically, when you take the dot product of two different unit vectors, it's going to be 0. In this case, again, going back to note 6, actually, we notice z with the dot product of r is actually going to be equal to cosine of theta. This is, again, given in note 6, so make sure you have those slides ready for in the exam. What is cosine theta in terms of this problem? Well, let's look here. Yeah, let's look here on the picture. What is theta in spherical coordinates? Well, we know phi is going to be the angle in the xy plane. This is phi. Theta will actually be the angle going between this yz plane or xz plane. It will be the angle going up and down, sort of like an elevation angle. This is theta. This is important because whenever we draw this out, because if we have, let's look at the yz plane, if we were to have it flat, we have y, we have z, and on the z we have a circular disc, so really it looks like a line looking straight, like horizontally. And we have our point charge here at the origin. Well, r is here. This is the distance r, given by our problem here. Now, r can be anything. R can be that line, it can be this line, it can be this line. It could honestly be this, straight up and down the shortest distance between 2 points. Now, r is going to be equal to, what is the distance r? We need this because, again, what is theta? Theta is this angle here. What do we know about cosine theta, if that's true? Well, cosine theta is equal to the adjacent side over the hypotenuse side. The hypotenuse side is the radius r. The adjacent side is, we don't know that. Or do we? The adjacent side is going to be the height. The distance, the z distance from the origin, or the point, I guess, this electrode, to the disk. That's the adjacent side. Well, what is r? R, if we look at this here, remember this is a right-hand triangle, or a right triangle, it's going to be the square root of h squared plus, well, we have to have the other side. We can't do this without it. The other side is going to be the radius of the circle, or a. Now, in spherical coordinates, they use rho, so we're going to use rho, but really this is going to be equal to a eventually. When, if you notice, when we take the integral, we figure that out. Now, r is going to be h squared plus rho squared. So we can plug that in. We can do this here. And cosine theta, this z dot r, this unit vectors, can now be basically rewritten in terms of rho and h. Now, rho is very important. We need this rho because we're going to be taking an integral with respect to rho. So we're going to come back here and we're going to plug this in. This is now equal to, well, I and 4 pi, they can come out of the integral because they're not part. We're not taking any type of, they're constants, per se. Now, the integral from 0 to 2 pi of d phi, we can kind of take this out because we don't have another phi in here, times the integral from 0 to a of what now? Well, rho goes on the top because of this rho here, divided by, or I guess here, times h, square root of h squared plus rho squared. Now the h, it can also come on the outside, right? So we don't have to have that inside. We can have this here. So we have IH over 4 pi, and then the integral of all this stuff. Well, the integral of d phi from 0 to 2 pi is 2 pi. So it's IH, 2 pi over 4 pi is 1 over 2. Now we have the integral from 0 to a of, don't forget this d rho, of rho square root of h squared plus rho squared. Am I missing something? Yeah, I am. This r squared here needs to be part of our integration. Why is that? Well, what did we say r was when we derived it over here? Well, we said r was the square root of h squared plus rho squared. If that's true, we need to make sure and not forget this guy. We cannot forget that guy because our integration will be completely off. So what is that guy? Well, we can multiply that here. What is h squared plus rho squared, or I guess the square root of it, squared? It's just h squared plus rho squared. Multiplying it using exponential form, this is 1 over 2. 1 plus 1 over 2 is 3 over 2. So this is really equal to the integral from 0 to a of rho h squared plus rho squared, 3 over 2 d rho. Of course, IH over 2. Now this is going to be in your table of integrals. This is something you don't have to memorize. It's just something you can look at from the, I'd recommend looking at past exams and putting down that crib sheet, unless I think he's actually posted a crib sheet on Canvas. If he hasn't, make sure and, do stuff like this. Anyways, we're going to get this. I'm going to skip a lot of steps here because this is a table of integrals. You can put this in your calculator if you want. H squared plus rho squared from negative to the power of negative 2 from 0 to a. And this is going to end up giving you eventually I over 2, 1 minus h over the square root of h squared plus rho, or a squared, sorry, And that is how, don't forget your units, that's how you do this problem. Hopefully this made sense. I think the hardest part in this problem is, of course, not forgetting this r squared, but also deriving that r. You have to know what theta is in the context of this problem. Anyways, hopefully this made sense. Hopefully you guys can work this out. Again, this is also very important. Look at note 6. You have to be able to do this. If you have any questions, please reach out to me. Otherwise, good luck.